right, let's just give everyone just a few seconds to kind of drop in, since we've got all these people waiting for us here. I don't know, will there be anyone to show up today? I don't know. All right, I think that's probably enough time. I don't know if anyone's actually going to come in, so let's just get this show on the road. Greetings, tech artists from around the world. It is 12:30. It is Friday. That means it is time for another episode of Tech Art Talk Live. My name is Chris, and I'm going to be your host for today's session. Now, for the last few weeks, we've been going on for exploring the very basics, the introduction of HLSL programming, or basically shader programming. Now, up until this point, we've just kind of, been scratching at the surface. We haven't really gotten into any kind of real shader work. That all stops today, because today we are going into the basic fundamental illumination model. And this is a little bit thing, so it's going to take 2 lectures. It's going to take this week's, and it takes next week's, and I'll explain why in a little bit. Now, if you notice, all of these lectures, as they are going along with the shading, build up on top of each other. So week 1 kind of was the support for week 2, which was texture maps. Now, if you want to, dig up that code from texture maps from last week and reuse it again this week, because we are going to use the exact same elements of it. But if you don't have last week's work, that is okay. We are going to do a quick introduction and go over all of that information really, really quick, just to remind you what's going on, where we go, and give us a place to start from in order to get a kind of like a fresh new place to launch from. All right, with that said, let's get this show on the road. All right, now we are going to talk about illumination models. And so this is the very basics of lighting. All right, now this is where shading really starts to get exciting, gang. All right, now, just plain out straight, here's the Cliff Notes version. Okay, when you're talking about lighting, we're talking about 3 illumination models. What we have here is the ambient, we have the diffuse, and then we have the specular. Okay, you'll notice that inside of my diagram here, a little plus sign showed up, because really what they're going to be doing is adding to each other. So when you add the ambient plus the diffuse and the specular, what you end up is getting the full-blown combined illumination model. Now it says Phong in there, and this is actually called Phong illumination, and we'll get by and we'll explain what that means. But before we do, let me make a bit of a disclaimer. Okay, this week we are going to cover, we're only going to cover the setup, how to get things going and how to move upon the work that we did last week. We're going to be going over ambient light. Actually, this is kind of a no-brainer. It's kind of simple, but we still have to go over it all the same. And then we're going to spend a lot of time on diffuse lighting, because diffuse lighting is really kind of like the most important component of all. Well, actually, no, I shouldn't say that. But needless to say, the ambient and the diffuse components are going to be everywhere. They're not only here in the simple Phong illumination, the basics of fundamental illumination, but they are also present inside of PBR as well. And so you'll see a lot of these same components in PBR, and it's good to have a good foundation for it. What we're going to do is we're going to focus in on this week just on these 2 components, and we're going to spend next week focusing on just the specular, or the 3rd component. Okay, now once again, this is called old school illumination. Now, a lot of folks might refer this to as Phong illumination. They may not know this is the old school versus new school. They just might say, oh, this is Phong illumination. Blah, blah, blah. Okay, it's named after a fellow. He was a research student over at the University of Utah back in the 70s. His name was Bui Dong Phong. And he was a CGI researcher at the University of Utah, and he created the mathematical approximation for the specular reflection of basic lighting. So in other words, he came up with the whole specular thing. But you said, hey, wait a second, I thought we were just talking about ambient and diffuse. This is true, but these are all part of what people in common colloquial call Phong illumination. And the nice thing about Phong illumination is that it's relatively fast and relatively it's quick to implement. Now, this might seem like a lot of work what we're going through today, but compared to something like the PBR techniques, this is very, very simple. And so this is something that we are going to have a nice strong basis on, and we're going to launch it out, and we're going to finish this through next week. Okay. Now, there are other more optimized approximations. We'll cover a little bit of that, especially when we talk about the specular components, but this is the basic simple model in order to get you started. Okay, remember, tune in next week where we focus on just the specular component, and we're going to go on the basic Phong specular optimization. So this week, once again, we are just focusing on ambient and diffuse. Okay, so let's start talking about ambient lighting. Okay, ambient lighting is what stuff looks like when it's in shadow. This is the darkest that anything in a scene can possibly get. Remember, do not color anything in your scene black. That is bad. The reason why that's bad, because when you dial things in black, then information starts to get clipped off. Now, a lot of modelers and a lot of animators work really, really hard to get their art to be seen on the screen. And when you have objects getting clipped, that means that stuff is no longer being visible, and then you can't see it, and all that work's gone to waste. So having anything go to black is definitely bad business. So ambient lighting pushes the lighting out of black into something like, okay, tiny bit of illumination, or what the color of an object looks like when it's in shadow. Okay, so whenever the direct light isn't shining on an object, this is what it's going to look like. All right, with that said, what we're going to do is create a brand new model inside SHaderEd. All right, so here's SHaderEd. Now we're going to continue where we left off last week, but instead of just assuming that you have it readily available, what we're going to do is we're going to kind of quickly go over everything that we've done up until this point, just as acting as kind of a reminder and get everyone on the same page. So I'm going to go over here to SHaderEd. I'm going to go to File. I'm going to go to New, Empty. All right, and I'm going to go ahead then in File, Save As. And then I'm going to go to this PC, my F drive, take Art EDU, take Artist Talk. All right, and then I'm going to save this over here. And then I'm going to call this, let's call this Illum Demo 1, because this is like the first one. Save. Okay, very good. Now we've got that going. So when we start with anything SHaderEd, we first start off by creating a shader pass. So I'm going to right click on where it's right over here, and it says create a shader pass. And then here's where the magic comes in. So let's call this one, just call it Phong, because ultimately this is Phong illumination. So I'm going to call this Phong. Change the name of the language from GLSL, change it over to HLSL. And for the vertex shader entry, label this one as, let's call this Phong vertex shader. And then for the pixel, call it Phong pixel shader. So we got Phong vertex shader and Phong pixel shader. We're going to click OK. Then we have it. OK, we've got the goods here. All right, we've got an empty shader file. We've got Phong in there. So we're going to need some geometry. So let's have some geometry to go with that. So I'm going to click on right click on Phong and go Add Geometry. Now this time I'm not going to add a cube. I'm going to want to add a ball. Balls show off lighting better than cubes do. So we're going to stick with a sphere, and I'm going to call this just ball. Click OK. All right, we are good to go. Now also what we need is a texture map. So I'm going to right click on Objects, and then I'm going to click on Create Texture, and then I am going to grab a texture that I think will be interesting. Let's see. oh, let's go with the evil eye. What the heck? Click on the evil eye. I'm going to right click on that. I'm going to bind this. I'm going to bind it to Phong. Okay, here we go. We are good to go, and so we have our infrastructure already saved up. I'm going to hit, I'm going to go ahead and save that. Very good. All right. Here we go. And so let's go ahead and grab I'm going to have to go ahead and change this. Hold on a folks second. Okie dokie. Let's see. Okay, where do we go into this? Okay, I don't want you guys to show off on that. All right, I'm going to move this on over to here. All right, so hopefully we don't keep on bopping back and forth and showing the stuff on SHaderEd. And I'm just going to have to do things the awkward way. I'm still learning my ropes around here. So thank you very much for your patience. Now what we're going to do is put our basic resources here. And we're going to first start off with the vertex shader. I always like to start off with the vertex shader because maybe that's because it's the first element in the pipeline. But I'm going to click on here and paste that in here. All right, so we're going to call this section our resources. We're going to call this our flip texture Y. We're going to call that 0. Why? Because we don't want it flipping. We've discovered that last week because for SHaderEd likes to invert its stuff, so we're not going to worry about it. But I'm going to still include the utility function all of the same, and our utility function just basically flips the coordinate of our texture map for us. So we've got to go here. We're going to create 3 new global variables. We're going to create the world, the view, and the projection matrices. Okay, these are going to go into the global, and so if they are global, then we need to change that and tell SHaderEd what to do with those global values. So I'm going to right click on Phong, move over to where it says variables, and then the only thing I need to change is where it says world, and I'm going to change that over to geometry transform, because that's what's going to happen when we transform our geometry to move around. We click OK. And that's move around. All right, so we've got that moving around, so everything is cool. And there's also one thing. Let's see, is this pinned? No, it's not. So I'm going to see if I can pin my thing. Okay, it's not going to allow me to pin this, and I'm just going to leave that in as okay. We'll get back into pinning just a little bit later. All right, so now let's go ahead. We've got that. Let's go ahead and put down our data structures. Got that going here. All right, here's our data structure. Now we're going to call this vertex shader input and vertex shader output. Now our input, we're going to get the object position. We're going to cast that to a float 4. And as a semantic, we're going to label it as position. We're going to get a float 3 normal. And we're going to get a float 2 for the texture coordinate. Now for our output, we're going to want the position, which is also a float 4, and we do have to label this with the semantic of SV position, and then float 2 we have with the texture coordinate, and we're going to label that with the just generic text coord. All right, we've got that going, so let's go ahead and make sure that everything is copacetic. No problems here with a save. And now I'm going to go to the vertex shader, and let's drop in the vertex shader. All right, now we have our vertex shader output, and we're going to call it Phong vertex shader, and we have our Vintech VS input in. Okay, now notice that it doesn't. This function doesn't have a semantic. Why? That's because on our output here, the position is called SV position. Now this is why this is because this identifies the shader as the shader that we're going to use. Okay, we're going to cast this. We're going to create an output VS output. We're going to cast this off to all 0. We're going to 0 everything out. And then the first step, what we're going to do is we are going to multiply the world matrix against the view matrix to get the projection matrix. And we're going to multiply that those 3 against the object position. So what this does, as a reminder, it transforms the vertices in local space, and it transforms them into world view projection space so that they actually show up on our screen when we want them to. And then what we're going to do is just recast our texture coordinates is onto here. And I don't think we're going to need this 2. but I'm going to leave that in there. So we left the 2 in there from last week so we could see our repetition a little bit, but I don't think we need that this week, so everything is going to be just fine here. So we've got our, oh, look at that. I goofed up again. I accidentally put this stuff inside of my pixel shader, and so I'm going to go and kill all of this and then put it inside of the vertex shader. All right, everything's good. Now we go back to the pixel shader. Yes. Okay, now what we're going to do is we're going to create our resources for our pixel shader. Now, things are a little bit different with the pixel shader than on the vertex shader, but it begins to make sense, and a lot of the stuff has to do with our texture sampling. So we're going to have to duplicate our vertex shader output, and we're going to cast that off as pixel shader input. Now here's our float 4 position. Remember, this is called SV position, and our float 2 UV, our texture coordinate. Okay, remember, in order to get texture mapping to work, we got to create a texture 2D object. We're going to call that texture map, and then we have to create a texture sampler, and we're going to call that, it's a sampler state, and we're going to call it color sampler. And then we're going to give it the filtering of the minification, the magnification, and the mipping, and we're just going to make them all linear. So that means it's pretty good. And so for the wrapping, we're going to call it address U is wrap and address V is wrap. So we're just going to repeat everything. But we're not going to be repeating anything here, so everything is just going to be nice and clear. All right, so we've got that going. So let's go ahead and add our pixel shader. And our pixel shader is right where we left off last week. We're going to return a float 4, and that's going to be for red, green, blue, and alpha. And notice that we're going to call it Phong Pixel Shader, and we're going to take the PS input in, so that's going to come in right from the vertex shader. And we have to create the semantic of SV target. It says that is where our output is coming from. This is where the color is coming from. This is the target color. So that's where it comes from. And to start things off, we're going to create a float 4 output. We're going to call it out, and we're going to cast it off as 0. And then we are going to just grab its color by accessing the texture map. Say, okay, texture map, give us a sample. And then as its inputs, we're going to say, okay, use the color sampler to sampler the texture, and we're going to want the in.uv coordinates for that. And we're going to give it to the out, and then we're going to return it. And so, whoa, look at that. Okay, there is our object here. And, okay, there is our object, and whoa. Okay, we've got lots of information here. This is a lot of crazy information. Now I want to see if I can somehow shift my texture coordinates down just a little bit. And so what I'm going to do, let's see, get texture into texture coordinates. So what I'm going to do here is where it says out.texture coordinate in my vertex shader. Let's see if this has any effect. And I'm going to go plus equals, and I'm going to go float 4, and then I don't want to add anything in the U. I want to add 0.5 in the V, nothing in this. Oh, and well, actually, oh yeah, I want to do nothing in the. Oh, that's right. This is a float 2, so equals a float 2. No, I want this to be float 2. Okay, and then I'm going to hit the semicolon here. And does that make things, that's a little bit funkier. Let's go with this 2.5. Ugh. I just do not like the way this is going at all. Okay, I'm going to have to try to find some kind of better way of addressing this. This is not just that pretty. But anyway, as we can see, here we go. And I am just going to, just leave that as is for the time being. We get the point. We get the. In fact, just leave it as is. Indecisiveness. All right, cool. So now let's start introducing. All of the ambient components here. Okay, hold on a second. I want to go ahead and introduce here. So we're going to deal with the ambient components here. Now remember, the ambient is what everything looks like inside of the dark. And in order to get things working like that, we first have to provide some kind of information. Like we say, we want to get information from the user. So we're going to create a new thing, a new context buffer, and we're going to call it ambient. And we're going to get the color that we want for ambient, and we're going to put it inside of the pixel shader. Okay, so let's get things moving here. All right, so we've got that working. Yes. Oh, wait, I want SHaderEd. Okay, now we have the SHaderEd. Okay, good. Okay, now we're working in the pixel shader here. And so what we got here is boom, 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 boom. Okay, too many windows to deal with here. All right, so we've got here, we're going to create a new context buffer just for the pixel shader. And then I'm going to put this right up here. And we're going to call it C buffer per frame, and then we're going to create this ambient color. Now here, look at this. We've got a little semantic here that's called ambient, and then we give it some just default values of 1.0, 1.0, 1.0. So this is what kind of it looked like. It does constitute as a struct. Okay, so I'm going to go ahead and save this. Now notice that this is a global variable now, and SHaderEd does not understand what the semantic of ambient means, so we have to give it some kind of indication of what to do with it. So I'm going to click in here, I'm going to go to variables, and then we have ambient color here, and we're going to leave that as none. And we're going to click OK on that. So the reason why I'm going to leave OK is because if we go over to this pin category, we now see ambient color is now tuned into there, and so we get to now choose our ambient color. So I'm going to click onto this thing, and I'm going to choose a very light kind of gray color, and let's go with something that can be seen, something around like here. Yeah, that should probably be good. All right, and now this is important for the alpha value, or the alpha channel for the ambient. Make sure to use the value of 1.0. Now this is very important, and you'll see why in just a little bit. Okay, now the only modification now we need to make is in the pixel shader. So in the pixel shader, we're going to leave things as is. We're still going to declare our output variable with 0, and then we're going to get our texture coordinate, like this, but instead we're going to call this out equals texture sample, texture map sample. Okay, and then here it is. We're going to do some magic stuff here. We're going to out. And we're only going to modify just the red, green, and blue channels. And so in order to do that, we're just going to say .rgb. So even though out is a float 4, we're only going to modify the red, green, and blue channel. And then we're going to go times equal. So that means it's equivalent to, well, it means with this, equals out.rgb plus, and then ambient color in this, but like I said, yeah, it doesn't really make sense here, so I'm just going to go times equals. All right, so that means it's going to multiply itself against this brand new stuff, and so here we're going to want the ambient color, and we only want the red, green, and blue channels. Okay, so that's why we only want this, and so the reason why I want this is because of this little factor here. We go ambient color dot A. So we want the alpha channel. So if we wanted to create some kind of transparency, well, the transparency is going to make our ambient color kind of transparent, but that's going to make it darker all the same. So when we do that, then it's going to diminish that. And so this is the reason why we start off with a value of 1, is because we want this to be fully opaque first. Because the more transparent we make it, we're going to make it darker. Okay, so I'm going to go ahead and save this. And you see that it got dark. And that's exactly what happens, because now our ambient color is this. If we were to go ahead and change our ambient color to something else, then we can see that it's changing along with it. And so our ambient now this is, it's kind of funky. Now you're never really going to get a red shadow unless you're like sitting on Mars or something. But in most cases, you're going to see kind of like a white and a kind of like a dark channel. So I'm going to leave this parked at right about here. And we're going to leave that. But notice that if I wanted to make it semi-transparent, then if I do like 0.5 to be like half transparent, we're going to see that it gets halfway dark. But we didn't see this. It didn't really get that much darker, but it's there. And we don't really see it mass-wise, so that's why I'm going to change this to 1. And if we remember, we're going to come back and start playing with this again. Okay, guess what, folks? That is ambient color. That is really all that there is to ambient light. Not very difficult. And so what we got to start worrying about is what we're going to do with diffuse. Diffuse requires a little bit more attention and focus. So let's get started with diffuse. All right, now diffuse lighting, of all the complicated shading models, it's in my opinion the simplest. And it really comes like this. Ambient lighting is just kind of flat, and it's not really shading. It's really just an offset you're putting onto the shader. So giving it, start with black, you're going to be raising it up just a little bit, and that's your ambient light. Now diffuse light, on the other hand, actually takes into consideration the relative angle between the light source and the normal in there. Just remember, the normal is that cranky looking arrow that sits perpendicular to the surface of your model, wherever it is, and that's going to give you diffuse light. Now other people might call this gradient lighting, and that's technically all the same, but gradient lighting or diffuse lighting, they're all kind of like one and the same. So how does this actually all work? Well, in real life, light is going to careen and bounce off the surface, and so actually no surface is perfectly smooth. I mean, certain metals and certain glasses are pretty darn smooth, but when you get down to it, there are a bunch of microfacets on the surface there. And so when light is emitted from a light and hits onto the surface, these little microfacets cause the light to kind of like bounce off in multiple different angles. Like, it is pretty uniform. And so this is actually how diffuse lighting is counting on these microfacets for kind of making all of the light kind of spread out. Now, because metals are smooth, then they really don't bounce light like that off, and that's why all metals are intrinsically black, because the metals get their color from the reflections, but because they're so smooth, the microfacets don't really reflect and spread the color around so much. So that is why the microfacets, make up the objects floating in material. All right, now here comes some math. Be warned, everyone. What we're going to be is invoking what's called is Lambert's cosine law. So in other words, Lambert's cosine law is this statement. It says the brightness of a surface is directly proportional to the cosine of the angle between the light vector and the surface normal. So in other words, look at this first look at this first image on the far left. You'll see that the light, which is in yellow, is coming directly down and pointed perpendicular surface. And look at where these arrows are going. And they're all very happy arrows, and they're all pointing in all sort of directions. But notice as we go on to our images going towards the right, the angle of our light starts to change and go from more perpendicular to more parallel. And notice that as the light becomes more parallel, these little arrows get smaller. Guess what, gang? That's Lambert's cosine law. So basically meaning the more perpendicular it is, the stronger the light's going to be. The more parallel the light is to a surface, that means the less light it's going to show. It's really that simple. Not too complicated. So you said math. This is like a good concept. It kind of makes sense, in your head. But where does the math come in? Aha. But be patient. Okay, here it comes, folks. Okay, now suppose that we have two vectors. We have vector A and vector B. If we were going to take the dot product of those, what we're going to do is we're going to multiply the the corresponding components of vector A and vector B, and then we're going to add them up together. So in other words, A dot product B equals x1 times x2 plus y1 y2 plus z1 z2. Okay, now that's standard fairly dot product, fairly simple. And then what we're also going to do is remember Oh, that's right. We never actually had a math class, or we did. It was so long ago, you may not remember. But there's this thing called the law of cosines. All right, the law of cosines says that c squared equals a squared plus b squared minus 2ab cosine. Okay, so what this does is if we combine this with the whole aspect of a dot product, we get that the dot product of a dot b equals the length of a times the length of b times the cosine of the angle between these two vectors. Okay? And so going from here, the law of cosines, down to here, takes a little bit of explanation, kind of like, I'll be happy to point this to a Khan Academy presentation where they go over it real well, but do you need to understand this as a tech artist? No, you just have to know that if you take the dot product of vector A and vector B, you're going to get the length of A times the length of B times the cosine of the two angles to that. So what does this have to do with the lighting? Okay, thank you for asking. All right, so what we're going to do is we've got our normal, which is that perpendicular line, that arrow that's sticking up kind of like perpendicular to the normal of the surface, and then we've got our light source here, and it's just shining down onto the surface. And so what we have here is the angle here. So this is the angle between these two vectors. All right, so if we have this normal here, which is our vector A, and then our source ray here, vector B, coming in here, then we say, okay, what we're going to do is we're going to say the illumination then equals to some constant k times cosine of that angle. So in other words, what we're going to do is we're going to say, what we're going to first do is we're going to make sure that the normal line and the coarse line, they're going to be normal vectors. So that means the length of the value is 1. And so that's why we go ahead and created this equation here as k times cosine of alpha. K is some kind of scalar kind. It doesn't even really need to be necessary. This could be 1 for all that matters. So the illumination of the surface really equals cosine of the angle. And that's really all that there is to it. Okay. Once again, we're going to assume that we're creating what's called as a directional light. We're not going to go into the difference between what a point light is and a spotlight and a directional light, but we're just going to assume we're working with directional lights. That's actually lecture is kind of like a little bit more advanced, and it's really long and it's kind of tedious. So we're just going to assume that we're working with directional lights, so it's keeping it nice and simple. And a directional light, in case you didn't remember, is like it's a sun or a moon or some kind of big old source of light, and it's sending out bazillions of light rays all parallel with each other, and they're all going in the right direction. And so the commonality is they all have the same directional vector. All right, so now that we've got that working, so let's go ahead and implement that into our code here. Okay, we're going to get my, all right, I'm going to get my SHaderEd here. That's going here. Okay, we've got our SHaderEd. Now let's go ahead and implement our, Fong here, our diffuse shading. Okay, but before we do this, there was one thing I forgot to do, and that we got to try to clean things up. All right, we've got this stuff here, and it's kind of like this is only going to get bigger as we get more and more involved. So what we want to try to do is move this stuff out of the vertex shader. Yeah, let me get this here. We want to move this stuff out of the vertex shader and put it someplace where it's going to be kind of simple and it's kind of basic. And so what we're going to do is I'm going to grab, where is my Sublime? Okay, we've got my Sublime here. All right, and give me a new file here. Okay, we've got a new file here. So what I'm going to do is I'm going to copy all of this stuff here. I'm going to click X to remove it and go into Sublime, and I'm going to paste it right in there. Okay, so it's real dinky and small, so I'm going to blow this up. Okay, please ignore what's going on inside of the, okay, there we go. Okay, so what I'm going to do now is save this as, now what I'm going to do is save it to the folder of where my project is, because otherwise Shader Tool or ShaderEd won't know where to find all this stuff. So I'm going to go my TechArt EDU, TechArtist Talk. I'm going to go at TechArtist Talk for this section, and all right, I'm going to drop this into shaders, and I'm going to call this common.hlsl. Okay, save. We got yes. Okay, so now we've basically pulled it out of the Vertex shader, and now we're going to put this into an external file, and we can use it again at some future date. And so in order to call it, what we're going to have to do is we're going to go include, pound include, and I called it common.hlsl, and then I'm going to hit save. Okay, it didn't bomb. It found it. Okay, this is cool. I was kind of having it to forget all this, but we got our common HLSL and we're including it, so we have now basically abstracted all of our information. All right, so we've got our vertex information. That's good. So what we're going to do, in addition to, before changing things around, we're going to go back to our Thong or our pixel shader, and then we're going to add another component to this, to our ambient color. Now what we need is our light color, and our light color is going to be just like our ambient color, so we're going to call it float 4. We're going to call this light color, and I'm just going to call this color, and then I'm also going to call the, oops, I'm going to give it a default value of, oops, I don't want that. Let's move this up over here. We go 1.0f, 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 and then 1.0f. Okay. Click on. Okay, notice that this is now, after I saved it, we have light color on here. So let's go ahead and punch in, oh, just plain old white for this, and then once again make sure to make that alpha value of 1.0 just as good. Not that it really matters too much, but it is kind of important. All right, cool. We've made the adjustments to our pixel shader. Well, we've made some adjustments. We've got our light color being entered into this, and now we can adjust our light color dynamically. Let's go back to the vertex shader and make our changes to the vertex shader. Okay. Now what we have to do now is we have to add another constant for our vertex shader. Just like we had the light color, we're going to have to add the light direction. Okay, so I'm going to click onto here. And there is another, I'm going to call this V buffer per frame. Now this is going to be another context buffer, and we're going to call it light direction. And we're going to call the light direction, we're going to make the direction equal to 0, 0, -1. So that means we're going to assume that the light is coming in, directly behind us. It is focused down the z-axis, way back in infinity, but since it's kind of like pointed at us, it's kind of pointed down the negative z-axis. That's why I'm calling this initial value of 0, 0, and -0.1. So I'm going to hit save, and it didn't quite capture that element here, so I'm going to change that to -1, and we are good to go. So this is the light direction. All right. Now with that said, let's go ahead and make our adjustments to our data structure. Now we're going to leave our input exactly the same. This is going to be a float 4 for our object position, a float 3 for our normal, and a float 2 for our texture coordinates. But now we're going to add information for our light direction, and we're going to have to add our normal position, because the normal is going to suddenly be very important, because remember, the normal shows up where it's perpendicular, and we're going to take the angle between the light direction and the normal. So we're going to have to add in those to our VS output. All right, so we're going to first put in our normal, which is a float 3, and we're going to call this normal, and then create a semantic for normal. All right, and now we're going to do the light direction, which is also a float 3. I'm going to call this light direction, and I'm going to call this text chord 1. All right, this is just like I say, it's kind of like a placeholder, but it doesn't really count for anything, but I'm going to go ahead and save this. Okay, so we have our vertex output now working correctly. And now we have these things coming from the vertex output. We're going to have to go and make these changes inside of the equivalent pixel shader input. So I'm going to copy these, go over to my pixel shader, and then drop those right into here. Okay, so let me clean this up a bit. Very nice. Okay, excellent. So now our pixel shader has got the input coming directly from our vertex shader, and they have the exact same data structure. Okay, we are good to go with that. All right, so we've got that going. So let's make the modifications to our vertex shader. Everything is going to stay basically the same, except we've got to do now with the normal position. So we have where our out dot position stays basically the same, and we have our out dot texture coordinate, that's ultimately the same. And okay, I'm going to leave this kind of like as we go here. All right, so now we're going to say out dot normal. Oh, that's not all caps, so it should just be normal equals. Okay, now first what we're going to do is we're going to convert our normal, which is a float 3, we're going to convert it to a float 4. So we're going to go float 4, and then we're going to go in dot normal. And notice that in dot normal is a float 3. And we're going to cast it off. We're going to just put in 0.0f on that. All right, so it's a float 4, and we're basically casting it off as in dot normal is the x, y, and z components, and the 0 is the w component. And because this is just a direction, we don't enable this with a 1, we label it with a 0. Okay, so we got that. And so what we're going to do then is we're going to multiply this against the world matrix. All right, so we're going to multiply. And we don't need that. And we're going to multiply the result of this against the world matrix. Okay, now we've multiplied the normal. We've put it inside of the world matrix. And so now we are going to go and put it back onto the normal. But the normal is only a float 3. So we're going to want x. We want the x, y, and z components of that. And so we got that. So this is all good and fine, but remember, what we want is the normal, but we want to normalize it. In other words, we want to change its length to length 1. So what we're going to do is we're going to sneak in one additional process in here where we're going to normalize this. Normalize, spelled that incorrectly, and we got one extra on that, and then we're going to normalize this, and then voila. We're going to leave that in there. So what we're going to do is all of that. So we've now processed our normal. We've converted our normal into world space. And now we've got the normal working properly. All right, gang, we got to move that. Now let's go ahead and do our light direction. So out dot light direction equals. Now we're going to use the light direction, but we're going to point it in the other direction. Right? In other words, we're going to make it point at us. And so we're going to go minus light direction. Okay, so that means is that it's going to be pointed right at us rather than kind of like going behind us pointing at our object. But we also need to make this unitized. So we want the vector coming from our light direction to be of length of 1. So we're going to normalize this one as well. So I'm going to type in normalize. right, get rid of that extra parentheses. Uh-oh, it says no such field as a light direction. Okay, what is my error here? It says light direction. No, oh, I misspelled light direction here. I gave it a capital I. Okay, there we go. So this are the adjustments to the vertex shader. So not a whole lot of changes. Now where the big changes come in are the pixel shader, of where now we have to do the multiplication, or we have to take the dot product of the normal and the light direction. That's going to give us our angle between those two vectors, and then we're going to take the cosine of that angle, and that's going to tell us how much light we have. All right, so we are in the pixel shader now. So let's go ahead, and we've got this. Let's make things a little nicer. We've got our output. We've got that very simple, made very simple. Okay, so let's go ahead and get our stuff in from the vertex shader. So I'm going to go float 3 normal equals, and we're going to, so this is kind of like a little place where shader coding gets a little bit voodoo-like. What I'm going to do is I'm going to take the normal of this again. So normalize in dot normal. Okay, the reason why I normalize this again, even though we normalized it coming out of the vertex shader, is because, remember, it doesn't go directly from the vertex shader to the pixel shader. It goes through a whole bunch of other gobbledygook, including the rasterization process. And then somewhere along that way, our normal vector may have been altered in such a way so that it's no longer 1 anymore. So what we're going to do is guarantee that it is a value of 1. So we're going to normalize it again here. Okay, and likewise, we're going to do the exact same thing to our light direction. So float 3, light direction, equals normalize in dot light direction. Okay, so now what we've done was we've taken our normal vector and our light direction vector, and we've put them into our pixel shader, and now what we've done was normalize them. So we said, okay, everything is now copacetic. And so what do? We're going to take the dot product of them. That's right, gang. We're going to take the dot product of them, and this is going to give us the value of the angle between them. So we're going to float n dot l n dot l equals, and it's very simple, gang. We don't even have to do the math ourselves. We can have HLSL do the math for us. So it's just dot of our light direction and our normal. Okay, so that's it. So there we go. So now let's go ahead and put all of that back into our equation. But before we put it back in there, where it says out here, I'm going to change this. Instead of just out right there, I'm just going to go out to float for color. And so that means it'll give me a little bit of something to work with. Okay, and then I'm going to change this one here to out, and I'm going to call this float 3. I'm going to call this ambient, because we now have our ambient component, and our ambient component is our AmbientColor.RGB times our AmbientColor.alpha. Okay, so that'll give us our transparency. And so let's take into consideration the light color. So color.RGB. Okay, so this is now the light color taken into consideration. Now this will give us now our ambient light. All right, so now we've got that going. So let's go ahead and grab our diffuse. So we're going to float 3. We're going to call it diffuse. And we're going to just zero it out. So I'm going to just call this float 3, 0. So what that's going to do is going to create me an initial diffuse value of float 3, make it all 0. And I'm going to just kind of move this up here. All right, so we want to make this shader a little bit efficient, so we're going to use a little bit of logic in here. And so we only want dot products that are somewhere between 0 degrees and 90 degrees. If it's anything more than 90 degrees, we don't want it. Anything less than 90 degrees, we don't want it. So we only want between 0 and 90 degrees because that's all our light can actually see. So ultimately, when we do the dot product of those two vectors, all we have to do is it positive or negative. So all we want is when it's positive. So if it's positive, that means that's what we want. So we're going to choose if n underscore dot underscore L is greater than 0. I'm going to put the parentheses there. Okay, we want to say diffuse. Oops, I misspelled that. Equals, we want our light color dot RGB times the light color dot alpha, just like we did for our ambient color. So, but this is our light color. And then we're going to multiply this by n underscore dot underscore L. And then we're going to multiply this by the color of our object. So color dot RGB. And there we go. And so we've got our ambient component. We have our diffuse component now established. So let's go ahead and combine them together. So now we're going to go, so out.rgb equals ambient plus diffuse. Okay, and then whatever the transparency of our object is, we're just going to leave it at that. So we go out.a equals color.a. And then we're going to return our out. Okay, I'm going to save this. Oh, we have misspelled here, and this should be called normal, not normal. It's like we got Noam Chomsky on here. So let's check this out. And n-dit-l. And so this is n.l. Oh, there we go. We now have an illuminated object. How do we know it's illuminated? Well, if we go over here, we look over here, and we're going to move the camera over, and we can see the sphere kind of moved over here. And so we can see that the light is right behind us, and it's moving. So if we wanted to change the light direction, now if we wanted to move it a little bit left and right, what we could do is kind of like go over here to our light direction in the U direction, and we can kind of move it to the left and the right. And likewise, we can move our light direction kind of like up and down. All right, so now you know it works. And how do we know it still works? Well, we got our light color. Now, even though the ambient color is still gray, we can make this now a light. Let's say if we wanted to make it a little bit, let's make it a little bit purple, a little bit magenta. There we go. And now as we see this, and it kind of like, it's still the diffuse value or the ambient value where it is in shadow. Right here, it's still kind of gray color. So that means is that we have a kind of like magenta light shining on our object, and it's casting a shadow onto the back here, and this is now light. Okay, though this is really, really cool stuff. We can still manipulate our ambient color, we can still manipulate our light color, and we can play all day with our light direction. Okay, folks, that is really all that there is. We just added our ambient component and our diffuse component. We combined them together, and we have our very simple basic. Now, we aren't done yet. No. We still have a little bit yet to go. And so what we have to do is deal with the specular component. Now, we're going to need an entire lecture to talk about the specular component because it kind of like is important, is what gave Bui Fong his namesake. But that is going to happen next week. Okay, so come back again next week. And where's our time for that? Yeah, let's get this. Come on. Oh, yeah. Okay, join me again for next week, and that'll be, okay, now notice that it's going to be at 12 noon. The reason why it's going to be at 12 noon is because I'm going to take my honey out for a a romantic weekend to St. Augustine, and so I got to leave a little bit early, and so we got to make the lecture next week at 12 noon. Not that it really is going to impact anyone who actually is attending, but in case you decide you do want to change, it is going to be on the 20th, which is like 7 days from now at 12 noon, and then we're going to be talking about 3D shading part 2, and that is going to be all about the specular values. Okay, gang, if you liked what you saw today, go ahead and subscribe to my broadcast, or subscribe to my broadcast on YouTube, or my name is Chris Rhoda. Go ahead and check me out on Facebook and on LinkedIn, and otherwise go to Art EDU and go to Facebook and on LinkedIn. Or if you're feeling really brave, go over to my website. That's at techartedu.com. Go ahead and drop in onto the website. I hope it's still working. Actually, I haven't been there in so long. But anyway, go ahead. There's a little opt-in button there. Go ahead and click on the Click Here Now. Leave your name, leave your email address, and I'll send you articles and emails and maybe goodies when they arrive, and if they ever do arrive. Thank you very much for joining me today as we explored the very beginnings of fundamental shader illumination. Join me again for part 2 of this illumination lecture, when we're going to be focusing just on the specular component. And until we talk about next weekend, until we see then, arrivederci.